This is your presenter Asloob Mudassar, and I am presenting slide number 52 of the course on laser physics. Question is, give a graphical representation of thermal activation and deactivation process occurring in a non-radiative process. How does the difference of energy delta E play its role? The answer is, thermal activation and deactivation processes occurring in a non-radiative process are governed by the following two equations respectively. That is, the first equation corresponds to thermal activation shown in red, and the second equation shown in blue corresponds to the deactivation process. These two equations have been explained in slide number 51, but I shall go through them very quickly. So here on the left hand side in the red equation we have B plus A star, which will give you B star plus A minus delta E. So here the particle B is in the ground state, the particle A is in the excited state. These two particles collide, and the result is that after collision the particle B gets excited, the particle A goes to the ground states, and this process requires some energy to be available for this process to be taken place, and this energy delta E is acquired from the system or preferably from the kinetic energy of the colliding particles. So this delta E corresponds to the energy taken from the colliding particles, that is particle B and A star. So this is explained, and this corresponds to the thermal activation. The second equation shown in blue is B star plus A before the collision will give you B plus A star plus delta E. And here B star is in the excited state, whereas A, the particle A before the collision, is under the ground state. So when the particle B star will collide with A, then what will happen? B star will go to B, that is it will go to the ground states, that is it will de-excite, whereas the particle A gets excited. So I have A star over here. So A star plus delta E, and delta E is the energy given off by the after colliding process to the system. That is, delta E may appear as the kinetic energy of the colliding particles, or may be preferably as the kinetic energy of the species A. Okay. So you see that in these two equations we are assuming that when B star, that is the energy attained by the process in B star, is greater than the energy attained by A star. That is, the excitation energy level of B species is higher in energy than the excitation of level A of the particle A. This will be explained further. Assuming a two-level system for non-radiative process, delta E is described as delta E is equal to EB minus EA, where EB is the energy corresponding to the excited level of a particle B, and EA corresponds to the energy corresponding to the excited level of particle A. And the difference is that it means that this difference delta E is positive, which means that EB is greater than EA, which means that the excited level in particle B has more greater energy as compared with the excited level in particle A. And these are the two energies corresponding to the excited levels of particle B and particle A respectively, and the difference delta E is positive. So delta E is the difference between the internal energies of the two species. The graphical representation related with these two equations is shown in figure question 52.1. So let's see this figure. So look at this figure. We have the picture corresponding to before collision, and we have some data corresponding to after collision, and on the left hand side we have the collision of first kind and also the collision of second kind. So let's first concentrate on the collision of first kind before collision. You see that the particle B is sitting in the ground state, the particle A is in the excited state, and you can see that the black spot is shown in the upper state in case of particle A, and the black dot is shown at the ground state in particle B. And this is the situation before the collision, and you see that delta E is the amount of energy shown between the excited level of a particle A and the excited level of a particle B. So this delta E is actually the difference that is required for the particle B to be excited. So you see that after the collision, as shown by the arrow on the right hand side, after the collision, we see that the particle B, we have the label with B star. B star, it means that B star means that the B is in the excited state. And you see that we have also shown that the black spot or dot is in the upper level, whereas the corresponding to the particle A, that which has D excited, the black spot is at the ground state. So this difference of energy delta E, which was required for the excitation of a particle B, is taken from the kinetic energy of the colliding particles. It means that the energy has been taken from the system. So we have shown it as minus delta E. Now let's go to the collision of the second kind. Consider the case before collision. You see that before the collision we have B star, which means that the B is in the excited state, which we have also shown graphically, and the particle A before collision is in the de-excited state because the black spot or the black dot is in the ground state. Again, you see that delta E is the difference of energy between the two levels, between the two excited levels. So this is the situation before the collision. So when they will collide together, what will happen? The B particle, the particle B will come to the will be de-excited and will come to the ground state, whereas the particle A gets excited, and we have shown it with A star. And so the difference of energy delta E will be emitted in the process. So we have shown this delta E by the plus sign. So we have a plus delta E. It means that this delta E is given to the system, and preferably to the kinetic energy of the colliding particles, and more preferably to the excited particle A star. So this is the graphical representation of first and second kind collisions. Now let's go back and read the next paragraph. From figure 52.1, it follows that the difference of energy between the excited levels of the two species must either be removed or added during the collision for non-radiative excitation or de-excitation to occur. So you see that again we have delta E which needs to be removed. For example, here in the first case, the delta E has been removed from the system. That is, the system, from the system, delta E has been taken by the collisional process, and that's why B gets excited in the first case. That is the collision of first kind. And you know that in the collision of the second kind, the delta E is given to the system in the form of kinetic energy of the system. That's why we have said that the energy is either removed, that is in case of the first kind, and the energy is added to the system as in case of the second kind, collision of second kind. So during the collision process for non-radiative excitation or de-excitation to occur. Okay. Now if delta E, this delta E which I have shown, that is the difference between the energy levels, between the energy of the two excited levels, between the energy of the excited levels of the particle A and B. This is delta E. So if delta E is much less than kT, kT is the thermal energy, the process is referred to as a near resonant energy transfer. In gas lasers, pumping mechanisms are sometimes based on this type of energy transfer. If delta E is equal to 0, an exact resonance occurs between the colliding particles. And from equation number 51.5, we can write KB star A is equal to KBA. And K was actually the constant which was introduced in the decay rate equations. When the particle, the first, which is B star A, is the constant which corresponds when the particle B, which was in the excited states, comes to the ground state. and the particle A is excited, and the KBA is the equation when the absorption takes place. That is the first K on the left hand side corresponds to the second kind of collision, and the K corresponding on the right hand side corresponds to the collision of the first kind. This is what we have discussed in detail in slide number 51. And these two equations these two parameters were related through the relation, that is KB star A is equal to KB into e to the power delta E over KT. And since we are assuming that delta E is much smaller than KT, then you see that due to this one, e to the power becomes equal to very close to becomes equal to 0. So e to the power 0 is equal to 1, and that's why we have written the relationship that KB star A is equal to KBA. Remember the condition that delta E is much less than KT. So you see that under this condition the process is referred to as the near resonant energy transfer. In gas laser, since this is important, this condition is important, that's why I am reading this paragraph for the second time. In gas lasers, pumping mechanisms are sometimes based on this type of energy transfer. If delta E is equal to 0, then an exact resonance occurs between the colliding particles, and under that condition we can write KB star A is equal to KBA. Or equivalently we can put delta E over KT very close to 0, and e to the power 0 is equal to 1, and and this relationship given over here also follows from the equation we have reproduced from the previous slide, that is the equation number 1 from slide number 51, equation number 5 from slide number 51. So let's move forward. The relaxation of D star into B results in the excitation of A into A star, as obvious from the collision of second kind, because over here B star comes back to B and A goes to A star. Relaxation of a B star into B results in the excitation of A into A star, which can result through back transfer reaction in the excitation of B. So you see that if consider the collision of second kind, and on the right hand side after the collision we have particle B in the ground state and the A is excited, is in the excited state. So A star must decay very quickly, because if it does not happen that A star is not going to decay very quickly, what will happen? The back reaction will take place, and this arrow can be inverted, the arrow of this reaction can be twisted by 180 degree, and then you will see that the reaction will be reversed. So we want to avoid the reversing of this process. So the relaxation of a B star into B results in excitation of A into A star, which can result through back transfer reaction in the excitation of B. So it means that if the process is reversed, then this B after the collision in the second kind will go back to B star. So the reverse process will take place. To avoid this, the decay of A, that is A star goes to A, should be very rapid. This is a desirable condition for the onset of stimulated emission process. For example, you can consider in these two species, you can consider the that is the for example, if two particles are present, that's a particle B and a particle A, and you may assume it to be 3-level laser or 4-level laser, where the lasing levels are the upper level of B and the upper level of A. The lasing will take place between these two levels, and then this the upper level of A star should be able to decay very quickly. So this rapid decay should take place so that the lasing process can take place, and the lower level is the population of the lower level is found to be smaller, much smaller in comparison with the upper level of the species of the species B or the particle B. This is a desirable condition for the onset of stimulated emission process. So we are writing this condition, that is ratio of Na star to Na is much less than the ratio of Nb star to Nb. That is the excited species of particle A, that is the excited species in particle A has a ratio to its de-excited species is much less than in comparison with the ratio of the excited species of a particle B, number of excited species in particle B to the number of unexcited species of a particle B. So under this condition we can avoid the back transfer function, or we can equivalently say that the back transfer process can be neglected, and the rate of decay of the excited species is simply determined by equation number 51.7, which we have reproduced over here from slide number 51, equation 7 reproduced over here. So you can see that the rate of de-excitation of the species in particle B in the excited state, that is d and b star over dt is equal to minus kb star A multiplied by nb star into Na. This equation has been explained well in slide number 51 also. So this is the end of slide number 52.